Hello students, welcome to Inside Physics. In this session, we will discuss the capacitive circuit. When an alternating current is given to a capacitor, the current flow will be alternating and we are supplying a voltage which is also alternating, which is called an AC voltage. So, what is a capacitor? It is useful to store the charge whenever we supply some potential difference to the plates of a capacitor. They will be charged, and whenever we require the charge, we can take it out from the capacitor and it is discharged to give out the charge whenever required in a circuit. So here I will give you a brief description of an alternating source is connected to a capacitor. We all know a capacitor is indicated by a parallel plate which is a positive electrode and a negative electrode, and there is a small gap between them, and the capacitance is denoted by C, which is measured in farads. Alternating current is supplied, symbolized with sine curve. This is called AC voltage supplied to a capacitor. Here we will formulate the current flowing through this capacitor. That means this is an capacitive circuit, a simple circuit with a single capacitor. So we all know the instantaneous potential difference across this capacitor is equal to V is equal to Q by C, right? We use the formula I is equal to rate of change of charge with respect to time. So to calculate the current in this circuit. So here what is this? Q is equal to Vc. We all know the instantaneous voltage here supplied to this circuit is equal to Vm sin omega t, where Vm is the maximum amplitude of the voltage. We all know that. We have discussed all these things in our previous sessions. Here I'll write Vm sin omega t C, which is equal to Q. So to get the current, we need to differentiate this. That means dq by dt is equal to, see this term omega t, c v omega, this will become cos omega t into omega, right? So here this term can be rearranged like this. Cos omega t can be written as sin omega t plus pi by 2. So this is current, instantaneous current is equal to omega c Vm sin omega t plus pi by 2. So here this can again be rewritten as, I am writing here, see I is equal to Vm by 1 by omega c, where omega is the angular frequency of the alternating current, C is the capacitance. Here you see I am taking this as a denominator in terms of reciprocal, 1 by omega c in the denominator, and besides there is a sine function which indicates the phase. Okay, so here this term looks like a impedance which is discussed in the LCR circuit, or this can be considered as a resistance of this circuit. So here I can write this same equation. I will write here I is equal to, from this I am writing here Vm by xc sin omega t plus pi by 2. What is xc here? xc is equal to 1 by omega c. This is called capacitive reactance. Xc is called capacitive reactance, which is similar to the resistance of a resistor. The dimension of this capacitive reactance is similar to the resistance which opposes the current in a normal circuit. Here also this capacitive reactance try to oppose the alternating current, and here acts as a resistance. So we see how this goes when we supply the current to the capacitor in the phasor diagram method. This is a phasor diagram. Already we discussed about the phasors. So there is a voltage, this is a phasor voltage which is a rotating vector. It rotates about the origin. If you take this as a origin, and this is rotating in the direction like this. So you observe the current which is ahead of the voltage by a phase of pi by 2. You can see that this angle is, this is perpendicular. There is a 90 degrees angle between the current and voltage, that is a phase difference of pi by 2. The current is ahead of the voltage. In the inductive reactance, inductive circuit, what we have seen in the previous session, the current is lagging behind the voltage. It is behind the voltage by a phase of pi by 2. So pi by 2 is indicated by a quarter cycle. Here if you take this sine curve as a full cycle, this quarter cycle indicates a phase of, see here, pi by 2, 0 to pi, pi to 2 pi. So that is what here the phasor diagram indicates. By phasor diagrams we can analyze the AC circuits, how the current and voltage are behaving and what is the phase between them. So here the vertical components of this current phasor and voltage phasor are shown here. This is the vertical component which gives the instantaneous current at this particular instant of time t1. When you consider the time at t1, which is at a particular instant with angular frequency omega, so the vertical component of this current, this is the vertical component and this is the horizontal component. So this is the vertical, this is horizontal. Again, if you consider the phasor current voltage, here the vector V, there is a vertical component and there is a horizontal component. This is the vertical component. Vm sin omega t1 gives the instantaneous voltage of this particular vector at a time t1. So this is about phasor diagram. This diagram, when they are rotating in anti-clockwise direction, we can have a graphical picture like this. So this is the maximum voltage Vm, and at any instant, particular instant omega t1, so the voltage is at this instant, the voltage is here, and at this particular instant you can see the current value which is given by this one, Im sin omega t1 plus pi by 2. You observe that the current is, this is the voltage, the red line is the voltage curve, and the current line, this is the black line, is actually ahead of the voltage line by a phase of pi by 2. This is the full cycle. If you consider from origin to 2 pi, you can take this as a one cycle. So we all know the average current or voltage in one full cycle is equal to 0. We already proved it. So this is the current, and we can write this as I is equal to I m sin omega t plus pi by 2. So this is the current, which is the instantaneous current which is passing through this circuit at a particular instant of time t. So here the power, we are all interested to know how the power is consumed in a capacitor when it is supplied with an AC current. So in inductive reactance, inductive circuit, we calculated the power and it has finally comes as 0. The power consumed is 0. Here also we will go through the relation with power, which is equal to P is equal to IV. So further we will calculate how much power is consumed in a capacitor. See, whenever there is an electrical instrument like resistor, capacitor or inductor, when a voltage, a potential difference is given by an external supply. So if it is a DC supply, the DC current flows for a very short time until the capacitor is fully charged. When it is fully charged, the current will be stopped. So for a short time this is having a full charging, and when it is fully charged there is a potential difference which is opposing the power supply. And this DC, when it is connected to DC, the DC power supply, whenever it is cut off, and this stored charge can be used to any other equipment where the extra charges are required in some electrical circuits. Now we are supplying with a AC current. So in AC current also, the inductive capacitive reactance will actually oppose the alternating voltage also, but it cannot prevent the charge flow 100%. It cannot prevent the flow of charge 100%. That is the difference between AC and DC. For now we are about to calculate the power here consumed in the circuit. So I is equal to, we all know, I m sin omega t plus pi by 2 into V. What is V? Here it is Vm sin omega t. So I into V. So that is equal to P is equal to Im Vm. This can be written as cos omega t into sin omega t. So when I multiply with 2 with numerator and denominator, this power will become Im Vm by 2 into sin omega t cos omega t. So this is like, from the trigonometric equation, this is nothing but sin 2 omega t. We all know sin 2 theta is equal to 2 sin theta cos theta. So this will be coming as sin 2 omega t. So I am writing sin 2 omega t in this place. So power is equal to Im Vm by 2 into sin 2 omega t, right? So the power, instantaneous power, has come to be this one. When we take the average, the total power in a particular time interval, we need to calculate the average. So the average power is equal to IMVM by 2. The average symbol is given like this, and we all know, we already derived how it becomes a 0 in our previous sessions. Sin 2 omega t, average of this sine function will be 0. So by this we can write the average power consumed across the capacitive circuit is 0. If it is 0, that means is there the power is not at all consumed in the capacitor? Does it mean the same? Yes, the power consumed will be on an average it is 0, because we will see the explanation for this also, how the power consumed is becoming 0 across a capacitor connected to an AC current. See, whenever you connected a capacitor to an AC current, so this is a positive side of the plate, and whenever the current is flowing in this direction and the current is on the positive side, we imagine that the current is on the positive side. So the positive plate to negative plate, and here the power calculation is IV. The current is positive and the current is increasing. So in the first quarter of this cycle, you just see what I am explaining. This is how it is increasing the current. See the current, how it is increased, the voltage is increased and it is positive, and in the first cycle the current will be, see, it is on the positive side and it is increasing. So it is positive into positive, the power consumption is positive. So the power is absorbed from the source. In the same way, in the second quarter cycle of the positive side of the current, this will be decreasing. The current again comes to 0 from the maximum. Here you see the current is coming to 0 to the maximum to 0, decreasing. When the current is decreasing and here the charge is also discharging, so the current will be negative. Here when the charge is decreasing, as per the formula I is equal to dq by dt, the current is negative and the voltage is positive. So the power comes to be as negative. So here the power consumption is consumed is thrown back, given back to the source. Okay. So next, here the third case, the polarity of the plates is reversed. That means the current is on the negative side. Here the negative side of the, this is the negative side, this is the positive side. So whenever we reversed the current, the polarity of the plates is also reversed and the current now it is increasing. The current is increasing. What happens on the negative side? The current is on the negative side. So here as per the power formula IV, see the current is on the negative side and it is increasing, it is negative, and the voltage, see the voltage is nothing but V is equal to Q by C, right? Whenever the current is on the negative side, the voltage is also negative, this becomes positive, power is consumed is positive, there is a definite value which is consumed from the source, so the power is positive. So in the next case, the last case, here the current is in the negative side and it is decreasing, the charge, it is, the capacitor is discharged, the current is also getting discharged. So here the current value will be negative and the voltage will become 0. So that means it is not a negative value, it is positive. So here the power consumed is negative. Okay, so the power consumed is negative means it is already, it is the giving back of the power to the same source, alternating source. So this is how in these four cases the power consumed is given back to the source again on the positive side, and on the negative side also the power, when the current is reversing its direction, the power consumed is also given back to the source, and on an average the power consumed on an average is equal to 0. This is how we understand the power consumption, and this is the analysis of the capacitive circuit which is provided with an AC current. So we will going to see the LCR series circuit in the next session. Okay.